Hey guys, so I forgot to record today's Zoom meeting, so I'm going to go ahead and make a quick video of what we covered in class today. It should be 15-20 minutes or so. So let's start with one of the things that I wanted to make sure to mention was fusion. Right, we've talked about fission. That's what happens in the nuclear reactor with the uranium-235, and we spent a whole day on that. So I'm not going to go into that. One thing we haven't talked about is fusion, right? And this is an idea that is commonly kind of passed around, and you'll hear about it, is that, you know, when you take hydrogen atoms and you throw them together, that they can actually fuse together, right? And if you take 4 hydrogen atoms and fuse them together, it actually creates a helium atom. It goes through some different types of decay and other radioactive things, but eventually it creates a whole lot of energy and a helium atom. And so much cleaner than fusion, right? Because the byproducts are safe. The byproduct is helium. The problem being is that fusion lets out so much energy that we don't know how to contain it, right? It puts out so much energy that it actually creates a 4th state of matter, which is called a plasma, right? You already know about a gas and a liquid and a solid, okay? But there's actually a 4th state of matter. That's a plasma, okay? And a plasma is when you take a gas and you heat it up so hot that the positives and negatives kind of dissociate from each other, and there's no interaction there. It's so hot, so much energy that it's not even like a gas where the particles are bouncing off of each other and interacting in that way. Everything is almost completely independent of each other because of how much energy is present there. A plasma will basically melt through anything that it touches, which of course is a problem if we want to be able to contain it and get energy out of it. So what they do is they have to contain it in an electromagnet and kind of suspend the plasma up in the air. The problem is that they have to put so much energy into that electromagnet and into that how they're trying to contain it that it actually takes as much energy or more to contain the plasma than the energy that we get out of it. And so it's a very inefficient way of getting energy because we need so much energy to be able to get that energy. Someday, hopefully, somebody will come up with a great way to control fusion and be able to get the energy out of that, because that would be the way of the future. It's a clean energy source. It's pretty easy to come across hydrogen atoms, so you could get a significant amount of energy from that in a very, very clean way. All right, so we're going to move on. We do need to talk a little bit more about blackbody radiation. Okay, so just a couple more things. Remember last class we were talking about blackbody radiation. We said, number one, that a blackbody is a perfect absorber. It will absorb all electromagnetic radiation, right? That's this note right here. It'll absorb all the electromagnetic radiation. We can't make a blackbody, but we can get pretty close. In order to be able to create a blackbody, you just take a box, right, like this. Before you close it in, you paint the whole inside of the box black, and then you close it up and you put one little hole right here in the middle. And so that one little hole will let light in, but because the inside is black, and you have to do it, it always talks about this in the textbook, it has to be matte black. It can't be glossy. Okay, glossy reflects light, which is not good. So it needs to be matte so that all the light that goes in this hole gets absorbed and none of the light comes out. Indeed, if you were to have a box like that that's painted black on the inside, if you were to look through the hole, you wouldn't see anything. It would be perfectly black because all of the light is being absorbed, which is what a blackbody is. So we can get pretty close, but not perfect. Now, an important part of discussion of blackbody radiation, we talked last class about Stefan-Boltzmann, which we'll come back to that and talk about that just a little bit more. But one of the things that we need to talk about is back in the late 1800s, early 1900s, there are these guys, Loomer and Pringsheim, who were trying to figure out when a black body has a specific temperature, what type of energy, what type of radiation is coming out. So not just how much. Stefan-Boltzmann found out how much power is coming out, right? But they didn't find out what type it was. One of the things that they knew is that a black body radiated all sorts of wavelengths, right? It was letting out visible light and ultraviolet light and infrared, right? Just like the sun is radiating out all these different types and wavelengths of energy. And they wanted to be able to calculate that. That's what scientists do. They want to be able to predict what's going to happen. So they tried using classical physics, and you get this, they got this graph over here on the right, okay? But using classical physics, this is the line that they came up with, okay? Now, really, these are the curves that you see. At 3,000 Kelvin, this red line, 4,000 Kelvin, the green line, 5,000 Kelvin, that's that's pretty hot. You're getting this blue line, right? And so they were able to predict at very long wavelengths what it would look like. But the closer we got to visible light, here's our visible light spectrum and here's ultraviolet. The closer we got, the farther our predicted line comes from the reality, which is what wavelengths were actually being emitted by that black body. And so they called it the ultraviolet catastrophe, because by the time you got to the ultraviolet, you were so far off. The classical theory predicted that the wavelengths would just continue to increase, whereas realistically, it did eventually kind of fall down. So it was called the ultraviolet catastrophe, which baffled physicists for a long time. A few years later comes along this guy, Wilhelm Wien, and he basically said, well, you know what? I can predict the curve. I can draw a curve using this formula right here. Now, this only works, though, if light acts as little packets of energy, if it's quantized. Okay, so he was saying that light wasn't acting as a wave, it was acting as if there were little bits and pieces of light that were coming through and landing wherever the light was shining. And of course, people said, that's ridiculous. We know light's a wave because of the double slit experiment and because it diffracts and because it refracts and all these other properties of waves. That's absolutely ridiculous. Therefore, we're not going to believe this guy, even though his model predicts what's supposed to happen. And so, several years pass, and then comes along this guy, Einstein. And Einstein says, hey, you know what? I think that light is not just a wave. I think that there are certain situations where it acts like a particle. And in fact, he's able to prove, using several experiments, that light in some situations acts like a particle. We're not going to go into that too much right now, because you're going to cover that in chapter 7 for SLs. That's part of the core. And then HLs, you'll get to do significantly more when you guys talk about the quantum physics in chapter 12. However, it is important to recognize that this nature of science thing, that for a long time, this law, Wien's law, was not believed, because he said the only way that we could get this to work is if light sometimes acts like a particle. And people didn't like that idea, so they disagreed with him, and and we stayed in the Dark Ages a little bit longer. So anyway, you can see this curve. I want to talk about this is the curve predicted by Wien. And you can see as the temperature goes up, 3,000, 4,000, 5,000, 6,000, that a couple of things are happening. The maximum of not the maximum, but the wavelength that happens most often, right? This is relative intensity. So this is the intensity of each wavelength. So the wavelength that has the maximum intensity is right here. For the green one, the wavelength with the maximum intensity is right there. For this one, the maximum intensity is right there. You can see that the maximum intensity moves to the left. Now, this should make sense, right? Because we're talking about a higher temperature. We know that temperature is proportional to the kinetic energy, the kinetic energy of the average kinetic energy of the particles. We also know that frequency is proportional to energy. We learned that we learned this one in chapter 4 on waves. We learned this one in chapter 3 on thermal physics. So it should make sense that at a higher temperature, there's higher energy, and at higher energy, there's a higher frequency. And remember, C equals frequency times wavelength, so a higher frequency means a lower wavelength. Therefore, lower wavelength as a max. Now, of course, higher frequency does mean more energy, so more energy means higher intensity. Intensity, by the way, is power per area, and we know that a higher temperature, what does that do according to Stefan-Boltzmann? Remember, power is proportional to temperature to the 4th power, which means a small increase in temperature is going to have a huge increase in the amount of energy, right? Doubling it, here's my 3,000, here's my 6,000 right here. The area under the curve is kind of represented, or the maximum peak of the amount of energy that's there, right? If you double the temperature, you expect 2 to the 4th, which is 16 times as much energy, which is why this 6,000 curve is so much more intense or larger than the 3,000 curve. All right, so this curve right here is what we call the Blackbody curve. And that's an important idea as we move forward, as we look at this. So you're going to want to be able to make connections between Wiens' law here, which relates the wavelength and the temperature. And then also, remember, temperature is in the Stefan-Boltzman law. And so you also want to then be able to make a connection from temperature to power or intensity. It's very common to get a question that starts, for example, with power. You get the temperature, which you then use to get the wavelength, or the other way, by knowing the wavelength, because wavelength is pretty easy to measure. You just have some type of sensor that measures that. Then you can measure, you use the wavelength to find the temperature. Once you find the temperature, then you can calculate how much energy is being put out by that object, dependent on its area. So this is an important idea as we start to look forward with various other things. All right. So I'd like for you to look at this and see if you can make sense, thinking of Stefan-Boltzmann, thinking of Wien, and talk about how it makes sense that each of these temperature curves has these particular shapes. Okay. I want you to pause the video, take as much time as possible as you need to, 3, 4, 5 minutes, to think about the connections between each of these formulas and the curves that you see here. Okay, go ahead and pause. All right, so hopefully you did that. So the first thing that we want to recognize, actually there's two big things, right? The first one from Wiens' law, as the temperature goes up, the maximum, the peak, when it says max, this is the one that has peak intensity, right? So as temperature goes up, the peak intensity should have a smaller wavelength. And we see that here, right? Here is the most intense right here, right? Here's the most intense right here. And here's the most intense right there. And you can see how the wavelength gets shorter and shorter. Now that should make sense because shorter wavelength means higher frequency, means more energy means hotter. Okay, so that's one thing we want to make sure that we're recognizing. The other thing is here, Stefan-Boltzmann, right? Increase in temperature proportional to the 4th power. So a small increase in temperature is going to have a large increase in the power. And so that's why over here on this side you've got intensity, which is power over area. Note that if I take Stefan-Boltzmann and I divide by the area, then I get power over area, which is intensity, equals Stefan-Boltzmann constant times t to the 4th power. And so it's directly related to that t to the fourth. We've got the p over a already here, which is our intensity there. And so then you can see how we're making the connection between a higher curve, higher intensity, is then because of a higher temperature. All right, that's really all I wanted you to get from this video. Make sure that you get that idea of fusion, because that's a common question that comes up, because it is contemporary and important for today, though that really is all you need to know about fusion for now until we get to chapter 7. And then secondly, make sure that you're comfortable with this, the Blackbody curve, and how it relates to both Stefan-Boltzmann and Wiens' law, and that should be enough for this. So hopefully you'll be able to use those ideas as you work on your homework tonight. All right? Thanks.